Okay, welcome to your first day of the second semester of senior seminar. The review this week is for classical physics, general physics, sorry. Yeah, classical physics, general physics 1, mechanics. So in mechanics, you should really think about it for yourself. Like, how do you bring it all together? What did we learn in mechanics? And what are the connections? So just think back to the chapters. I know it was a long time ago, but the chapters in your basic physics text, right? We start with kinematics. So we start with kinematics. Kinematics. What is kinematics? Kinematics is the relationship between your kinematic variables, the variables that describe motion, um, acceleration, velocity, position, and time. And in kinematics, we basically just define acceleration. Acceleration is the rate of change of velocity, derivative of velocity with respect to time. And we define velocity as the rate of change of position, dx dt. Um, and this is one-dimensional kinematics. And from those two definitions, we can determine the kinematic equations. And that simply comes from the two definitions. It comes from integrating, cross-multiplying by dt and integrating, and you get delta x equals 1 half at squared plus v0t, and you get v equals v0 plus at, and then if you combine those two equations, you get v squared equals v, to cancel out time, you get v squared equals v0 squared plus 2a delta x. So there's only two unique equations here. There are three equations that I tend to use in kinematics relating the variables. Now, sorry, that relates to the kinematic variables. So then we say, well, okay, that's one dimension, but we move into chapter 2, which is vectors and the fact that we live in a three-dimensional world, and we know that therefore you can write these same equations for the y direction. And that also means, sorry, that we have to put subscripts, right? So now if we move into a multi-dimensional world, this is the acceleration in the x direction, the initial velocity in the x direction, etc. All these have sub x's on them except for time, because time is not in a particular dimension. And then we have the same three equations, 1 half a sub y t squared plus v0 yt dot 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 in the y direction, and the same three equations in the z direction, no matter how many dimensions we have. Okay, so that's chapter 2. Chapter 3 is two-dimensional kinematics. Chapter 4. Then we move, what comes after kinematics? We come to why things move, as opposed to the relationship between the movement variables. We come to Newton's laws. So Newton's laws tell us why things move. Things move because, things can move if you exert forces on them. Newton's laws. Primary thing here, other than the concepts of Newton's first law and third law, you can review those yourself, is how to apply F net equals ma. All the concepts are important, but in terms of solving problems, how do you apply F net equals ma? So Newton's laws is Newton's second law problems. Then what comes next? We actually have about 3 chapters on Newton's laws, 4, 5, and 6, where we define all the different forces and the fact that, right, there's a frictional force and a normal force and a tension force and a spring force and all those forces. And then we say, but there's another way of looking at things. Nice thing about the other way of looking at things is it's not vector dependent, and that is from an energy point of view. So energy conservation comes next, chapter 7-ish. And again, it doesn't matter what chapter number, but approximately chapter 7 and 8 are work and energy, or energy conservation concepts. And there we define kinetic energy, potential energy, work, total mechanical energy, conservation of energy, non-conservation of energy. Oh, and I tend to write KEPE, but the right way to do it is kinetic energy is K and potential energy is U, usually. This was work and mechanical energy. Okay. So the energy conservation, okay, so kinematics is how do we relate the motion variables to Newton's laws, is how do we create motion. Energy conservation is just a different way of looking at creation of motion, but it also brings in the concept of conservation, which we really couldn't do science without understanding conservation. Um, the fact that there are quantities which don't change. And that brings us to the next topic, which is momentum conservation. Momentum conservation. And of course, that comes from Newton's second law, right? Because Newton's second law is really F net equals dp dt. That's really what Newton wrote. And momentum conservation tells us that if F net equals 0, therefore dp dt equals 0, therefore p doesn't change. Not that p is 0, right? Therefore p doesn't change. P, which equals mv, does not change. So that's just another conserved quantity that helps us to understand why things move the way that they do. Okay, so that's the primary basics of general physics in the first semester, classical mechanics, except that we have one additional topic. And the additional topic is, I didn't leave myself enough space here, so I'm just going to write on the side. The next topic, if you remember, in classical mechanics that bridges us to the next semester is rotational mechanics. Rotational mechanics, rotational kinematics and dynamics. Is mechanics. Mechanics is kinematics and dynamics. Kinematics and dynamics. Okay, so sorry I'm writing on top, but I'd rather not go to a new slide because I want to refer to some things here. Now, rotational kinematics and dynamics is a big subject because it talks about kinematics, Newton's laws, energy conservation, and momentum conservation, all in rotational variables. But in reality, it's not a big subject, right? Because rotational kinematics is simply saying, oh, well, if instead of moving a straight line, linear motion, which we have done up until chapter 9, instead of linear motion, we're now going to say rotational motion, but the rotational motion works the same. So where in linear motion we had delta x, in rotational motion we have delta theta. We go through an angle theta. In linear motion we had v, in rotational motion we have omega, angular velocity. And as long as we know the relation, as long as we know the variables the variables in rotational motion that correspond to the variables in linear motion, then there's nothing more to learn. Because all you have to do is say, we can now just take any equation in linear motion and rewrite it in rotational motion. So where delta y is a position variable, then delta theta must be a rotational variable. Where a is a acceleration in linear variable, alpha is the acceleration in rotational variables. And time is still the same, and omega 0 t. There you go. So we have kinematics in rotational variables. And we don't have to worry about x, y, and z because we only talked about kinematics, rotational kinematics in one dimension. So we don't have to worry about rotational kinematics in multiple dimensions, which is very complicated motion, right? The precession of a top, for example. A spinning top. So, and then, things like, and that's kinematics, and then rotational dynamics, where we had, I'm just going to write over to the side, where we had F net equals ma. Well, in rotational kinematics, rotational dynamics, we had F, force is like torque, so we have torque net. Mass is like rotational inertia, and acceleration is angular acceleration. Torque net equals I alpha. So as long as we know the variables, we know the equations. Nothing new to learn. So that's a pretty concise, right there, one little whiteboard summary of all of Physics 115. And it is, and there's nothing more to learn, but you really do know how to apply these to solve problems. So let's do a couple of examples. I'm going to do a couple examples starting with a kinematics and Newton's second law problem.